Okay. So what did you put for number 8?
Oh, true.
But I didn't put mine. Okay, it'll be false. Number 8 said, if a collision occurs in an isolated system, then any object involved will conserve its own momentum. That is false. The total momentum of both objects before the collision will be equal to the total momentum of both objects after. But the individual objects do not conserve their momentum.
Can you explain that one just a little bit more?
So like, what's one of the examples we were doing yesterday? With the cart and the brick, for example. The brick's momentum changed. It was 0 and then it's whatever was moving after that. The cart's momentum also changed. It was going fast and then it slowed down. But their combined momentum at the beginning and at the end, if you add them together, is conserved. Conserved means it doesn't change. Okay. Alright, number 9. What did you say for number 9? False is correct. Forces always will come in pairs. Okay, remember we talked about that when we were doing Newton's laws of motion. That even though it doesn't seem like it, even if we push down on the earth and it exerts an upward force, it's also exerting a force on the earth as well. The reason the earth appears not to move is because that its acceleration is so small that it can't even be perceived by us. It would be almost 0. Because it's so big, the earth is so big. Okay, number 10, who do you agree with? Ben, good. Because the mass of the bus is so large compared to the bug that the change in velocity of the bus would be almost 0, just like the change in velocity of the earth. Okay, number 11. C, good. The recoil momentum is going to be the same as the momentum of the bullet that it fires. Number 12, who can explain why it's necessary for airplanes to push the air downwards?
I said that way the change in momentum going up is equal to the change in momentum down and
Okay, good, yes. The mass and velocity, which would be the momentum, mass times velocity, of the downward air will equal the mass and upward velocity of the airplane. So if it pushes the air down, then the airplane will go up. Okay, so 13 sort of is an explanation of one of the multiple choice questions that we talked about the other day. Does anyone have an explanation for it?
There's no opposing forces that it's momentum? Maybe?
Well, what if it's like in space and it needs to like go? It's like stuck there. And it needs to move. Why?
You're saying like the energy from like the, I don't know, like the flames, like
Yes.
will push it up.
Yes. So it's actually the mass of the fuel that's coming out And I don't know, I read this somewhere, the oxidizer, I don't really know what the oxidizer is, but something about the flames and the fuel that comes out the back, will equal the velocity, the mass and velocity of the rocket moving forward, so that would be why. Okay, so what about Kent Swim? Why would this not be a good idea?
If he fell, he would drown.
That's true. Why would he fall though?
Because when he jumps, he's also exerting a force on the boat which will push it farther away from the dock.
Okay. Yes. So maybe he won't fall, but by the time he gets on the dock, the boat is not going to be near the dock anymore because when he pushes off of it, the boat is going to push in the other direction. Good. Okay, 15A, both B, both C, both D, good, E, good, F, good. Okay, and did you guys, how did you do on the tables? Did they make sense to you?
I guess.
I guessed.
Yeah.
I
Yes.
got answers.
Okay.
Yeah, I got answers, but I guessed.
Okay, so what was the total for Kent before the explosion? 150. So what do we know about the total after the explosion? Has to be the same. So it has to also be 150? And so the boat would have to be negative 50. Yes. Yes. Because the totals have to be the same. Is that what you guessed? Yes? No?
I tried to follow a pattern that we did, and like multiply and like divide, and it didn't.
So you
work
did
out.
a lot of
We
work.
did it right.
Okay.
Kind of.
Okay, that makes sense.
Okay, so for B, the cannon and the ball, what's the total before the explosion? 126. So we know that after the explosion, it would also have to be 126. I think it's just positive 9 in that case for the ball. The ball would just be 9. Yes. Okay. Questions? Alright. We're going to go through a couple of demonstrations of this.
You sound like a little.
It's actually nice.
Do physics outside.
It'll be
I'll
nice
outside.
somewhere else.
Yeah. It's me 70 next Wednesday.
Really?
It's
It's supposed to be 70 on Easter.
Oh, good.
Maybe we can go.
Easter. Why? Because we're at church. We have rehearsal?
I'm not used to staying until 3:45.
Yeah.
Oh.
I think you're done from the early
Okay.
No, and then we have a technique class that we have to take.
Alright,
So,
So,
it's optional.
we have a
It's
car.
extremely recommended.
No, it's not optional.
Ladies. We have a car and we have a truck. So the car's mass is 1,000 kilograms and its velocity is 20, and momentum is mass times velocity, so it is 20,000. And then we have the truck, whose mass is 3,000. It is not currently moving. You can't really tell that by the picture, but its velocity is 0, and so therefore its momentum is 0. So then, what happens when the car rear ends the truck? Okay, so the car's velocity is now 5, and so its momentum is now 5,000 instead of 20,000. And the truck, now, what happened to it?
Its velocity is now moving at the same rate as the car, so its momentum is higher.
Okay, good. So it wasn't moving at all, and now it is moving at 5 meters per second, and so now its momentum is 15,000. So prior to the collision, what was the total momentum? Do you remember? 20,000. After the collision, what's the total momentum? 20,000. Okay, they have to be the same, right? I think that's really the end of that. Okay. Let's do another one. So we have, this is the cart and the brick.
It's like Mario.
It's physics.
Mario.
Okay, so to begin with, the cart has a mass of 3, a velocity of 50. This is centimeters per second. And so the momentum of the cart is 150. The brick has a mass of 2, its velocity is 0, and so its momentum is 0. Yes, it's just floating in midair. And then after, now the velocity of the cart is 30, and its momentum then is 90, and the brick now has a velocity also of 30, and its momentum is 60. So again, before the collision it was 150, and after the collision it is 450. Okay, good. So we get the idea. Here is the real life example.
One of the carts, the red cart that you see in the center of the video, has a mass of 750
Oh, this isn't the cart, this isn't the cart and the brick.
kilograms. The blue cart, which will be moving into the scene, has a mass of 0.250 kilograms, or 200 kilograms. The collision will be an inelastic collision in which these two carts stick together and move as though they were a single object after the collision. So before the collision, all of the momentum will be concentrated in the blue cart, which has a mass of m. And afterwards, together, the two carts have a mass of 4 times the original mass. The 3m for the red cart and the m for the blue cart add up to a total m of 4m. So the collision looks something like this. In the background of this video, you'll notice that we have a position time graph. And the position time graph was obtained by setting a motion detector to detect the motion of the blue car. And somewhere around this point on the graph, we observe that the collision takes place. The velocity of the blue car, as represented by the slope of the line, changes dramatically at that point. We can use the tools of this program in order to determine the pre-collision and the post-collision velocity of the blue car. Right here is the moment just before the collision. And if I use the tool that calculates the slope of that line, I will find that the blue car was moving before the collision with a speed of approximately 0.5022 meters per second. After the collision, right around here, the speed of the blue cart and red cart was the same, and we can determine its speed by using the tools of this program. And what we find is that after the collision, the speed is then 0.1295 meters per second. This is roughly 1/4 of the original speed. This proves to me that momentum is being conserved. That before the collision, the blue cart with a mass of m had a velocity of v, which was about 0.5022, and after collision, the total momentum was concentrated in both carts, which had a mass of 4m and was moving with a velocity of roughly 1/4 v. The 0.1295 is roughly 1/4 the 0.5022 meters per second.
Why do you have to use such small numbers?
I don't know. That software is pretty cool. Okay. Let's go through the multiple choice. So, a large truck and a small car have a head-on collision. Which vehicle experiences the greatest force? C, the force is the same, good. Which experiences the greatest impulse? Good, the impulse is the same. What about the greatest momentum change? Momentum change is the same, okay, good. A ball is thrown upward from the ground with 5 kilograms meters per second of momentum. With what momentum will the earth recoil and why?
B.
A.
Okay. Alright, a lineman tackles the fullback in football. Their before collision momentum is shown below. What is the after collision momentum of the lineman fullback combination? Think about the direction.
Oh, yes.
A.
Good. Okay, bumper cars A and B have a collision. A before and after collision vector diagram is shown. What is the total momentum of the system?
I'm kind of confused.
Do you add the two together?
So what do we know about the total momentum before and after?
It's the same.
It'll be the same. And we don't know what the momentum of car B is afterwards, so we just can look at the before and find the total momentum in the before collision, which would be D, 5. Does that make sense? That's why they have it like that, because now, what is the change in momentum of car A? C. And what's the change, or what is the after collision momentum of car B? Good, how did you know it was C?
Because if you add 3 and 2 is 5, and then 1 times 5 plus 3 times 5 is 5.
Good,
That's the same momentum.
very good. What would be another way we can think about that? If car A is losing 1.5 units of
Gaining
momentum,
1.5.
and car B would be gaining 1.5. So that would be another way to look at it. Good. Okay, a baseball player holds a bat loosely and bunts a ball. Express your understanding of momentum conservation by determining the values of A and B in the table below. A would be 40, and so B would be 30. Good? There are 2 A's at the bottom because they would be equal to each other. Because the total momentum would be the same. Okay, a Tomahawk cruise missile is launched from the barrel of a mobile missile launcher. Okay. Express your understanding by determining the values of A and B in the table.
B.
Good. So before the collision, if there was 0 momentum, then after the collision there will also be 0 momentum, and so the launcher must be negative 5,000. In an effort to inflict the most, okay, this, you're not gonna read that. I'm done with that
We're referring to the
question.
previous question.
No, okay, no, we're done. Alright, that's enough of that. So let's look at the last page of your packet. I would like to look at number 19 with you guys, and then I'll give you some time to finish up the rest on your own. Alright, so 19 says if a 5 kilogram bowling ball is projected upward with a velocity of 2 meters per second, then what is the recoil velocity of the Earth? So how are we going to determine that?
Figure out the momentum.
Yes, and momentum is what?
Like what's the value?
How do we calculate the momentum?
5 times, or the mass times change velocity?
Okay, good. So we'll have the mass, just velocity. That would be change in momentum. So we have the mass and velocity of the bowling ball, and that will equal the mass and the velocity of the Earth. They would be opposite, but we're not concerned about direction in this particular problem, so we don't need to make one negative and one positive, but they would be going in the opposite direction. So the momentum of the ball would be the 5 times 2. And so to calculate the velocity, we know the mass of the Earth is 6.0 times 10 to the 24th kilograms. And multiply that by V2. So solve that for velocity by dividing and so what will that give you? Did you do 10 divided by that?
Mm-hmm.
Mm. 10 divided by 6 wouldn't be 6. Why? What's anybody else getting?
I got 1.667 to the negative 24 or something. I don't really know.
I have 8.3. I mean times 10 to the negative 23rd, or 25th, but the number in the front should be. Where is that coming from? Why did I write that down? Okay, I don't know where that comes from. Yeah, it would be 1.67, I guess we'll say, times 10 to the negative 24. Meters per second. And so that means that there is 24 zeros, actually 23 zeros before we get to the 1, right? So 0.0000, so that's how little it's going to affect the Earth, which is why we don't see that the Earth is moving. Okay. Alright, go ahead and take the rest of the period to finish the back. Hopefully you can get it done before you go, if not, we'll just have a little bit of homework for a long weekend.
Can I swap here?
Yes.
On 17B, does the after just stay the same since there's only one arrow?
Yes.
Well,
Yes.
can you explain number 20? Like, I got the information off the thing drawn down, but
I don't know if we're overthinking it or.
Did you have to calculate the momentum of each player.
We did that.
Okay. And so you should have 240 going to the left and
Mhm.
640 going to the right.
Ooh, we have 160.
80 times 8.
Oh, oops.
I believe I made that same mistake. We just did it. And then